analyzing yet another rational function. Going through our procedure, let's see how this one starts to look like. So first things first, we will see if we can factor. So let's look at this. I have f of x. To me, it looks like the denominator is a little quicker to address. X squared plus x minus 2. Factors of 2 that add up to positive 1, or factors of negative 2. That does factor nicely. So we should have x plus 2, x minus 1. And I also have 2x squared plus 7x minus 4. And that would mean if we're looking at factors of, let's see, 2 times negative 4, I might have to take a little work off to the side. So factors of negative 8 that add up to 7. That is 8 times 1 with a negative 1. So we know it's factorable. The issue is, though, we know that because we have a 2x square, we know that the factorization is going to be a little different than how we factor the denominator. We can break it down into binomials, but the only way to make a 2x square is by having a 2x times x. But let's test this out with the bottoms up method, because these numbers that you choose right here are not going to be in this full factorization. So let's take a little time on this. When I say 8 and negative 1, because my a is equal to 2, I can divide both by a to help me out with the bottoms up method. So that's going to leave me, if I reduce, I have 4 over 1, and negative 1/2 did not reduce. So bottoms up method would give me x plus 4 and 2x minus 1. So now I can go back and say, aha. So I think I put the 2x first in this case, so I'll attach that in, 2x minus 1 and x plus 4. So we do have our numerator factored completely and our denominator factored completely. Important things to note right away. There were no common factors, so you could also address that there are no wholes. You can kind of write that down. Or if the problem were to ask, you would probably say none. So sometimes you might see it this way, where you'd have to address that. And I think they would say wholes. There we go. The next thing to double check is let's look for vertical asymptotes. And with our vertical asymptote, we do realize, looks like we're going to set our denominator, x minus 1 times x plus 2 equal to 0. And right away, we have solutions to that equation. We should get x minus 1 equals 0 or x plus 2 equals 0. In other words, x equals 1 or x equals negative 2. And again, remember, these are both vertical lines. So we actually have 2 vertical asymptotes. Let's include those. At x equals 1, I'll label it, and x equals negative 2. So right away, our rational function is going to be quite interesting. Okay. Next thing, we're going to address, do we have a horizontal asymptote? So let's see. Let's compare those degrees. So I'm looking at the original function and looking at the leading coefficients. It appears the degree of p of x is equal to the degree of q of x. And again, reminder, remember we talk about p of x is the polynomial in the numerator, q of x is the polynomial in the denominator. And in both cases, their degrees are equal. They're both 2. So that means we do have a horizontal asymptote. It's at y equals, and remember what we did is we take the leading coefficients. So it's always the leading coefficients of, let's see, 2 over 1. Here we go. So we can reduce that. 2 over 1 just gives us a 2. So again, this is a horizontal line, don't forget. And let's add this in our graph. So y equals 2. All right. Now, because we did find a horizontal asymptote, right away, we know that we don't have a slant asymptote. So we can address it by saying that there is none. So we're good to go there. And what we want to do for ourselves is now look for maybe some other key characteristics like the intercepts. So I'll label that work over here. And x-intercept, that's going to have us set the y value, or f of x, equal to 0. Normally, I would say look for our reduced function, but we don't have one. But I'll take the factored version. That might be a little easier for us. So let's see, our factored version, 2x minus 1 over x, times x plus 4, all over x minus 1 over x plus 2. So that's going to equal 0. Now, again, the same sort of argument we've been talking about this whole way through. When you do have a single fraction equal to 0, we can then set our numerator equal to 0. That's the only possibility to help us out. And now we have a quadratic equation. Well, it's been a quadratic equation. So we can set 2x minus 1 equal to 0 or x plus 4 equals 0. And solving both of these equations, we should have x equals 1/2 and x equals -4. So if you want to think about what these look like as ordered pairs, you don't have to. If you plot them correctly, you're not needing to understand that their y value is 0. We already said it. But let's plot them in our graph. So 1/2 would be about right here. And then I believe it was -4. So we have our x-intercept. There's 2 of them. Next thing is to look for our y-intercept. So again, with the y-intercept, I'm going to set my x value equal to 0 or find f of 0. And however you'd like to do it, I probably wouldn't use my factored version. I think it might be a little quicker for my, my original function, mainly because I know that a lot of terms cancel out. So I'll kind of show you just so that you can have that experience. But you would see 2 times 0 squared plus 7 times 0 minus 4 over 0 squared plus 0. I believe it's a -2. Remind myself one more time. Yes. So what is really happening is all the terms in x are canceling out, and you have -4 over -2. Or in other words, you have, we're going to simplify this, a +2. So if you were looking at the ordered pair, the x value is 0, the y value is 2. So we can plot this in our graph. And that's interesting. Look where we landed, right on our horizontal asymptote. So let's take our TI out to help us see what our graph is behaving like. I think if we didn't have a calculator, you're going to have to pick a lot of x values to see the patterns a little nicer. So I'd have to probably see, what's happening after the vertical asymptote, x equals 1. But lucky for us, we do have that technology that we can bring so that we don't have to spend a lot of time with the tedious computation. So we have our previous graph here. Let me zoom back to standard just in case. And then I'd like to enter my new function. So I'm going to clear everyone out and remind myself, again, I'll put my original function. I should have 2x squared plus 7x minus 4 divided by x squared plus x minus 2. Ooh, careful there. Got a double negative on accident. So let's see how the graph looks. You can kind of see, okay, there's where our functions are. So I can copy and paste this, or just so that we can have a nice accuracy here. I mean, I guess you can't do this if you are just using paper and pencil, but we'll utilize our technology and we'll try to draw the accurate graph. So I'll try to paste it kind of nearby so that we can have that. I'll draw a little bigger for you all. Okay. So if I was trying to copy this, what I'd like to do is maybe see that it appears the way the asymptotes are. You could kind of guess what's going on, but I could draw in. Looks like y equals 2. There's my horizontal asymptote. So that gives me an idea that it looks like there's something going on like in the middle of these two asymptotes. Do our best. And that also gives us a clue. If we're looking at our other asymptote, x equals +1, you can kind of see that your graph would be hugging it a little bit on the right. So something like so. Doesn't look as smooth. Try my best. And then also at x equals -2, you could kind of see, oh yeah, it has the same sort of idea, but it has to cross through -4. So let's make sure we have this. And we pretty much have our graph. And actually, I should go back, and you probably didn't see anything we drew. So let's repeat ourselves one more time, just in case. Sometimes I have problems switching off, but let's go back. I just copied and pasted my graph. So I'll kind of reiterate for you all one more time. Not bad to see a repeat, right? So let's remind ourselves. We drew our horizontal asymptote. It's at y equals 2. So I could kind of see what's happening. Also, if I'm looking at my vertical asymptotes, they were at x equals 1 and x equals -2. So you can kind of see what's going on with the blue curve. And so I'll kind of reiterate this one more time. I know you probably saw it, or you're like, no need to, but it helps. So a reminder, I'm just kind of looking the way my blue curve is working. It looks like there's some sort of reflection or symmetry in a sense in the upper right hand side and also the lower left. So I have to cross through -4 because that's my x-intercept. So I can kind of see that going on. And then in the middle of the two vertical asymptotes, we seem to have something that somewhat has an inflection point. But we're not worried about that at this time. But we do know it has kind of like, it has like a cube, x cube sort of feel to it. So we'll do our best to kind of make that curve happen. And that's what I'm trying to do, is just emulate what did I do on my calculator as accurately as possible. Now that you can see that, the one last thing I'd like to address is you don't really have to go through the mathematics to determine if your graph crosses your horizontal asymptote, because you can see it cross like right in front of you. If you wanted to, you would notice that we already kind of figured it out already, but at 0,2, which is our y-intercept, it's at the horizontal asymptote. So feel free to explore that if you want to prove it to yourself analytically. But for our purposes, when we have our TI, it's kind of nice just to say, okay, yeah, it crosses, we're good. So I hope this helps. These take a lot of practice to get good at. So that's what the homework is for. So take some more time on that, and hopefully these examples will help you out. I'll see you in the next section.